Hello, everybody, and welcome back to hypothesis testing of the mean via if we have the sample standard deviation. So let's look at example 2 here. A local brewery wants to ensure quality control and that 12 ounces of beer was in each marked bottle. The manager sampled 48 bottles and found this group's average to be 11.72 ounces with a standard deviation of zero point 0.6 ounces. So, part A, is there evidence at a 5% level of significance that the true average amount in the bottle is different from 12 ounces? So, first of all, this is a hypothesis test because most hypothesis tests start with is there evidence? If I wanted you to find the sample size, I would say find the sample size. So this video is going to be a little different. This video, I want to take you step by step into which I, as a teacher, would want everything displayed for a perfect 100% on a project or a final or a midterm question. So I'm going a little different here. So here we go. I know it's a hypothesis test question because the is there evidence. If I wanted a confidence interval question, I would say build a confidence interval. If I wanted a sample size question, I would say find the sample size. I would check out my previous videos on confidence intervals and sample size to see what I mean by that. So, all right, here we go. And in real research, you know what you want to build because you are the person building the research project. I'm the one controlling this as the professor right now. So, okay, is there evidence? That means hypothesis test. So when I have a hypothesis test, I like to go to my formula sheet and I like to look at all the hypothesis tests in my first level of statistics class. So you have this Z distribution one right here. And then you have the T distribution one right here. And it's all depending on do you know the population standard deviation sigma or do you know the sample standard deviation S? When we read the question again, we will note we have the sample standard deviation, and that's why I will utilize this set of formulas. So again, back to our question. It says right here, the manager sampled. Standard deviation is 0.6. Manager sampled 48 bottles and blah, blah, blah. Standard deviation is 0.6. That is probably the most important characteristic is I have the sample standard deviation. Because I have the sample standard deviation, I know I will be looking for the t values. Everything will be based on the t distribution. That's so important to me. All right, now let's go through the steps of a hypothesis test, shall we? First off, what are we looking at here? The true average amount in the bottle is different from 12 ounces. Normally, when you ask your question, you state your alternative. So that's what I get from this question, the alternative. The true average amount, better known as mu, true average, population average, mu, is different from, not equal to, 12. And in fact, that's what I'm going to write here. In my step 1, my H naught, my mu, the true amount of alcohol in, not alcohol, but beer in the bottle is equal to 12. And the alternative, because that's what comes from the question, the alternative is it's not equal to 12. So I'm thinking this as a quality control type of question. I believe my machines are working properly and I'm getting 12 ounces of beer. Unless you show me some evidence to shut down the factory and display, oops, we're in trouble. So ounces here. That's the units of measure. So that's a perfect first step. Now we just go through and isolate every important variable that we have. Since we're using the T distribution, the T distribution comes with the following letters. N, S, and X bar. And you can look at the formula to see those letters are important. So these are the four variables, I should say, I'm looking for. Well, alpha is the level of significance. Back to the question. 5%. Level of significance, please place it as a decimal. N is sample size. That's important. Our sample size here is what? Well, we sampled 48 bottles. There's your sample size. S is the sample standard deviation. Well, we needed that because that's the controlling device of why we are using the T distribution. So 0.6 is a sample standard deviation. The average of the sample was 11.72. Now, where do these numbers come from? These numbers come from Excel or anywhere you can build your descriptive statistics. So what you would do is you would take 48 beers from the factory, you would measure them out, and you find the average. So I can imagine 48 beers just being labeled out. This one has 11 ounces, this has 11.2 ounces, this has 12.1 ounces, all the way down, just a list. I would average that list up to get 11.272 ounces in my sample, and I'd find the standard deviation via formula of 0.6 ounces. So I know how to get these numbers in the descriptive box. They give me the numbers I need in my data set. And alpha comes from the question, from the research. So these are all important variables that I had to ascertain. If you're good with Excel, you can obviously put most of this stuff in Excel to help you out. Like we have a two-tailed test. How do I know it's two-tailed? Because it's a not equal to test. That's important to me. Mu, what is the stated null hypothesis? The stated null hypothesis is we have 12 ounces of beer. I'm going to assume the machines are running at 12 ounces of beer unless you can tell me otherwise. What's my level of significance to reject that? 5%. All right, let's do the study. How many beers are we going to sample today? 48 beers we take off the machines. And we measure out each one, how much how much beer was in each one. We average up those 48 beers, and we found 11.72 ounces with a standard deviation of 0.6. Here's the big question. Is 11.72 that far away from 12? That's really what it comes down to. Is 11.72 ounces that far under 12 for us to shut down the factory and say, as quality control, one of our machines is not working right and we need to fix it? So that's what the rest of the analysis will do, is to determine, is 11.72 that far from 12, or is it within what we call the acceptable range of quality control? All right, let's get to it. So in my steps to do, the first thing I always do is write all this down, my null, my alternative, and the information that I need. From here, so this is kind of like my step one, if you want to call it. And again, on my projects, on my midterm, on my final, I want these details, all right? If you're watching my videos just to learn how to do it, thank you, welcome. But right now I'm really trying to dive into what a Dr. McCullum complete answer would be, okay, guys? And I'll try to spell it out in the steps. Step 1, give me the null alternative. Step 2, label all relevant information. Boom. This is very relevant because this gives me the t-distribution. Step 3, build the critical region. All right, how does one build the critical region? Well, here we go. We have the t-distribution. We just talked about that. When you have S, you're going to work with the t-distribution. Which one? Recall, degrees of freedom is always n minus 1, so this is the t47 curve to me. Degrees of freedom is a way to deal with bias in the advanced calculus courses you could take in grad school, and you can exactly find the perfect t-curve to work with. In this case, the t-curve at 47 degrees of freedom. All right, how do I know how to draw my picture? I isolate this and this. Those two key pieces of information give me my critical region. The not equal to means 2 bars. The alpha is how much area is outside of the bars. So back to my picture. 2 bars because of the not equal to, and 5% is outside. Total outside. And so that means I have 2.5 each time. What I would do is write down what I'm doing step by step in your own words to help you out. That is so critical when it comes to these videos. All right, take your time, write it down. It's a complete solution. So this is kind of like a complete solution guide to help you study for the midterm, final, and projects. I want these steps. These are important steps to me, and to determine whether I DNR, do not reject H naught, or if I do reject H naught. That's what it's all about right here, is if the number I get falls in the blue region, my test statistic falls in the blue region, I will say I'm in quality control. If it falls into either red region, too little beer in the bottles, that's going to be customer complaints, so don't want that, fix the machine. Too much beer in the bottle, I'm not happy as the boss. Come on, guys, don't give away the beer, all right? So there's a fine line between in quality control and out of quality control. And that's all bounded by a t value. And that's the t critical value. And by symmetry, it's the same number on both sides, just positive and negative. So how does one find it? So once again, you just need to make notes of how you find these numbers. To find a critical value, it's always by t dot inverse in the t distribution. If we were using the z distribution, I would do norm s inverse. All right, this is the t distribution, so I'm using t dot inverse. All right, what do I put in t dot inverse? Well, in t dot inverse, you put the probability below the bar you're looking for. Well, the area below this bar, the area below this bar is 975. And you think of it because what's the area above the bar? 2.5%, which means the area below is 97.5. And then again, I got to tell Excel, these are Excel codes, by the way, which T-curve to pick. That's why the degrees of freedom is so important. It tells which T-curve to do the advanced calculus on. And there you go. That is my T critical value. All right, back to Excel to find that. And so I'll put that, where's my critical value? Right there. T critical value. That will be found by T dot inverse. Probability below, we discussed 975. Degrees of freedom, and we can even try to automate it, right? Degrees of freedom will be n minus 1. We can always have fun and try to automate our code, so if we change something up top, everything flows with it. For example, you see how we got an answer, and that's a beautiful answer. 201 is our answer, but it's not completely automated because I used 0.975. Let's think about some advanced Excel skills, if you like, here. How could we make this work with those first 5 numbers, right? The first 5 numbers are the ones that will change. I don't want anything else below to change. I want everything to be based on those. So what I would do is, I see the 0.05. And so what I would do is 1 minus this number divided by 2. Because I need to take this number divided by 2 to get 2.5, and then 1 minus it to get the 975. If you notice, exact same number. You do not have to do this. What I love to do is automate my work. So if somebody says, no, oops, I didn't mean alpha was 5%. What I really meant was alpha was 10%. Aw, man, do I have to go back and do all the analysis? No. If you can automate certain numbers, these numbers right here, if you can automate, that is, these are the numbers you're going to ask the client for. You're going to ask the client for what was the old average? What is the level of significance? And then you're going to collect data. So these are your numbers. From all these 5 numbers, I would love to fill all the rest in. So how do we do that? Well, first we start with the critical value. The critical value is again based on area below the double bar, which would be 975. So I had to think about how do I get 975 from an alpha of 0.05, comma degrees of freedom, which is n minus 1. So at any time, I would pause, right, and think about how I got it. These are how you will really get really good at playing with Excel. So 201. That is just a side cool part of learning statistics, is learning how to command Excel better. So there's my T statistic. That's this number right here. That's the bar I have to pass. If my statistic gets past this number, I'm going to reject. If my statistic stays in here, it's safe. If my statistic falls below negative 201, I will again reject. If I reject, that tells me I'm out of quality control. I need to fix the machines. If I'm in here, I state I'm within quality control. Things are good. Maybe tighten up the machines, maybe a little bit, but I'm not in the red region, so I'm happy. So here we go. Now that I have my critical value, I can find my test statistic. So here's my critical value. Now I want my test statistic. How does one find the test statistic? Well, that is a formula. The test statistic is on your formula sheet. Should bring that up one more time. Let you pause and let you take a picture of this. If you're in my class, you have the formula sheet, and you should always have it handy for test and projects. There's your test statistic. It's the mean minus the national over SM. S sub M is right there. So allow me to write that into my steps. it is going to be x bar minus mu. And yes, m and x bar to me are the same thing. M mean, x bar sample mean are the same thing, okay? Divided by s over radical n. That's your test statistic. All these numbers, x bar, s, and n, are your sample. You're comparing your sample to the national levels. That's what you're doing. Your sample compared to the national statistic. In this case, the national statistic is your label. Your label is a 12-ounce beer. How in control is your sample based on your label? Guess what? Good thing up here, I wrote down N, S, X bar, and mu. Mu, N, S, X bar. All I got to do is drop it into this formula, and I have my test statistic. All right, friends, it's Excel time. Why don't you pause the video and try to put in your test statistic? All right, we're back? Cool. So we're back. And by the way, as you're watching my videos, you should have this Excel file open. I gave you this Excel file if you're my student, which means you can look at and fill in these blanks. I don't have the answers for you. I give you the blanks so you can fill them in with me, so you can learn how to do it. So I'm going to do the test statistic and automate it. Well, the X bar was 1172 minus the national statistic 12. I hope everything from, again, the green down, I can code in. So if I change one number in the green, everything updates just like that, instantaneous. All right, now I got to be careful. I have S, sample standard deviation, divided by the square root of N. And there's my code. I'll bring that back up so you can take a look at it. So there's my test statistic. Now, by the way, I'm not worried about this test statistic. Yes, it's negative. I knew that's coming in, that it would be negative. My sample is under average. My sample is 1172. So right away, I knew it was under average. The question is it too far under average? Now that I've calculated the test statistic and I know the critical value, I clearly see this as, wow, my test statistic is well under the negative option of this critical value. And I can go back to my picture. So my test statistic, once again, 2 decimals. Oops. Negative 3.23. Just making sure. Negative 323. Awesome. And so my conclusion to this question is my test statistic, negative 323. Well, let's look at the region. Negative 323 is way over here. Remember, this number is negative 201. Negative 323 is less than it, which means we could even highlight it. There it is. That's negative 3.23. And that's in the rejection region. All right, this number is the green number. That's in the rejection region. So is in the critical region. That implies I reject H naught. And we're done. I clearly reject H naught. Now, of course, you would put in some big statement about what this means. We will do that at the end because I'm going to continue on and build a couple other things. But I want you to understand you are truly done with what we call a critical value hypothesis test. As your teacher, I don't know what path you're following, psychology, sociology, marketing, management, you name it. Statistics is in all levels, all walks of life here at college. So, and it doesn't matter what you go into, but it does in some respects because some people do the critical region, which I just went through. Some people prefer the p-values, and that's what I'm about to do next. They are checks of one another. So either way, you will get the answers. You just got to be careful. So step 6, and yes, on the test, I'll tell you what steps to do. In real life, you got to decide which approach you're using, and so just use it and just validate it. Step 6, the p-value approach. So the p-value approach, if asked to do it, you once again draw your t-curve. It's a not equal to, so that's true. But now, in a p-value approach, what you do is you take your statistic, negative 323, your statistic. The p-value is the area outside of your test statistic. And that's a positive, I know that. That's a positive 323. That's a negative 323. The p-value is once again the area, total area outside of those bars. All right, so how would one find the total area outside those bars? That's a darn good question. That's what I call a test 1 question. We're now on to test 2 material here. In test 2, to find it, you would utilize the fact that you know how to work with the t-dist function. The dot-dist function is perfect for p-values. If we're looking at the z-curve, I would do norm s-dist. Because we're looking at the t-curve, we're doing t-dot-dist. Do not mix norms and t in any darn question. If it's a t-curve, do t-dot-inverse, t-stat, and t-dist. That's very important. Do not mix these up. All right, so the p-value, first of all, is double because of the two-tailed test. Now, I want the area outside of this. So I want the area outside of this. Now, I happen to have this number as my t-statistic, right? So if I find the area outside of this and double, it's the same thing. Because I have the negative, it's actually easier to deal with it. Because I have the negative, what I'm going to do is do t-dot-dist. And you know what? We're trying to automate it. We're trying to push you a little bit. The easy answer, let me continue on the easy answer, would just be, since this is the number I have as the statistic, I just drop it into t-dot-dist, tell it the degrees of freedom, and yes, it's always cumulative when you're doing basic statistics. And that will give you the answer, because t-dot-dist will tell you the probability under a bar. Since this is the number you gave me, the area under this bar would be this red region. If you double it, you get total both sides, and that's what you want. Again, the p-value in a two-tailed test is doubled. You need to know it's a two-tailed test from the not equals. So we can code that in. So that would be a nice, simple, straightforward answer. I'm going to code it so I can completely use Excel again if something happens. So I want the p-value. So I know it's going to be 2 because of the not equal to test. Now, here's the thing. Typically, you get a positive t-statistic, a test statistic that's positive. So I'm going to assume that test statistic above is a positive number, and I have to deal with it. And if it's negative, how can I adjust for it? So it's a game of logic and understand how to code this correctly. So 1 minus, because if I had the positive end, I want the area above it, and the t-dot-dist would give me the area above it. But this is negative, so I want to make it positive. There is a function out there that always makes things positive, and that's the absolute value. So if I take the absolute value of this number, it's always positive. The absolute value of a positive is positive. The absolute value of a negative is a positive. So no harm, no foul. The absolute value will take the t-stat and always make it and keep it positive. And that's awesome. Degrees of freedom? Well, that's n minus 1, so I can use n minus 1, comma, cumulative, always a 1. And so that would be the formula I would use. Let me just pause there and give you a chance to look at it. Or you should pause the video and make sure it makes sense to you. You could, of course, use the exact thing I just had and got the answer. Nothing wrong with that. I'm trying to automate this utilizing the green numbers. So if I change the green numbers, everything else will change. The green numbers change the test statistic. If the test statistic change, that changes the p-value. And that's awesome. I like to automate it so I have all the particular things I need right in front of me. And so there's my p-value, 0.0022. That is my p-value. My p-value is 0.0022. As a decimal, remember how to move things to not as a decimal, as percent. As a percent, that's 0.22%. P-values are usually in percent form. So there's a 0.22%. You can rerun this experiment and get the same result. What does that tell me? Well, my conclusion based on this is under pretty much any alpha I'm going to give you, right? The lowest alpha I have is 1%, and that's under 1%. The alpha we have in this question, recall, the alpha we have in this question, going back to the beginning, is 5%. We clearly are under the 5% threshold. I'd like to add on, it's under the 1% threshold, which is usually the strictest we go for alpha. Typical choices for alpha are 1, 5, and 10%. It clears the 1% hurdle, so no matter what, you're going to reject no matter what. And that's the idea. If you're under alpha, you reject H naught. I want to make that clear. Under alpha, you reject H naught. If it's equal to or greater than alpha, you do not reject. Please understand, whatever conclusion you got up in the critical region, so we rejected, better be the same thing down here. They don't swap, guys. If they swap, you've done one of them wrong. That's up to you to figure out which one you did wrong and fix it. All right? I mean, the only time it would swap is if you were so close to alpha. This was like 4.999%, so dang close to alpha. There could be some weirdness going on in your numbers, and you would need to hold accuracy all the way through, extreme accuracy all the way through. That would be the only time, is if you'd have to be dead, almost dead on to alpha, and that's the only time you might flip-flop, and you still shouldn't. That's when you got to hold true to your accuracy if you're that close. We're nowhere near alpha, so it's a thundering reject both times. That's very important to me. All right, guys, so we're back to work. And what we have here, we've rejected twice. So, again, everybody has different steps when it comes to hypothesis testing. We just did the critical value approach. We just did the p-value approach. We rejected twice. So right now, what I would do, depending on the steps, and please just follow the steps I have on the assignment. You skip the steps I don't need, you add the steps that I do need. All right, there are many, many steps, and it all depends on what is needed. So, conclusion. Actually, I'm going to pause on that. It's too early for me to conclude, actually. I apologize. 2 steps I'd like to include, or maybe even 3 steps. So 6. So we're on step 7. Step 7 would be a confidence interval. Now, which confidence interval do I build? I kind of set this question up ahead of time. I wanted the 90% confidence interval. And you would only build a confidence interval if you reject. The reason being is if you reject, that means you don't believe in the national number anymore. The question is, since you don't believe there's 12 ounces of beer in the bottling I've been doing, then how much is in there? That's what the boss is going to ask. All right, so you think there's not 12 ounces. How much is in there? And so I can say, well, 90% confidence, this is how much is in there on average. That's what I want to build, a 90% confidence interval. How does one do that? You look up your formula sheet. And right in front of us, here is our confidence interval. Your confidence interval for mu, because that's what you're trying to capture, is you don't believe it's 12 ounces. That's very important. If you reject, you don't believe it's 12 ounces anymore. You believe in this case it's probably under 12 ounces. The question is, so with 90% confidence, can you tell me how much alcohol is in there on average? Of course, I can take a look at the confidence interval. A confidence interval is X bar, your sample average, plus or minus some error. What is the error? Well, the error in this case will be the T marker times S over radical N. Do you always build a confidence interval? No, you build it if needed and if asked on my assignments. I like to build them if I reject. That's the only time I build them. I build confidence intervals if I don't trust mu anymore. When do I not trust mu? If you reject. If you reject, you give me suspicion to believe that mu is different. Let's check that out. Now notice, we have X bar, N, and S already loaded. All we really need is the T value for a confidence interval. Well, let's review that. Again, this is all about teaching you how you should do it on a test or a project. Giving me so much information, I know you know what you're doing. So for a test, midterm, final, or project, please follow these steps, the articulate steps. I'm trying to be very, very clear in each one of these steps for you to use. So 90% confidence goes into here. I want this T value. That's what that is. That number right there, that T is this T. You find that T, you plug it into the formula, we're done. So how do we find that T value? Well, look at the picture. We've done a bunch of these now if you followed my videos in order. And to find a critical value in the confidence interval, it's always T dot inverse. To be honest, the only time I use T dot dist is in a P value. If I want a confidence interval, I'll use T dot inverse. Well, now you got to remember the area below that T bar. The area below that T bar is 0.95. I'll let you think about why I know it is. And then, of course, degrees of freedom. And so I find that number. That is the T value I need for my confidence interval I want. All right, back to Excel. So 90% critical value, or sorry, 90% confidence interval. And yes, I will tell you the confidence interval. Your boss will tell you, do 90, do 95, whatever the boss wants. I'm your boss in this case, and I want 90%. So a 90% confidence interval, you're going to use T dot inverse, the probability. So in this case, it's preloaded with the 90%. So I know it's always going to be 0.95 for that. Degrees of freedom is not always the same number. Degrees of freedom is based off of your N, your sample size. Remember, we're always trying to automate things. It is always going to be 0.95 in the 90% confidence interval. So that's a good thing to know. 90% confidence interval, it's always 0.95 underneath that T bar. Once I have that T, then I can go about building the rest of my formula. What is the error again? Well, the error, my friends, is your T value times the sample standard error divided by the square root of your sample size. I want to be very clear and articulate in the number I want. That is your error. The back end of the confidence interval is always your error. And there it is. And then once I have the error, I can utilize that to find my lower bound. And the lower bound is your sample. Please, guys, your sample minus the error. And your upper bound is your sample average plus the error. And that's my confidence interval. So, once again, checking out the codes. First, it is going to be T times S divided by square root of N. And that gives me 0.145. Then the lower bound is the mean minus the error. And the upper bound is the mean, sample mean. I got to make that very clear. Sample mean. Remember, we rejected. So we're relying everything on my data. My X bar, my sample. I don't trust mu anymore. I rejected that mu. So back to the work I'd write down my T value, which, over here is 1.68. And then, of course, here's my formula. So I can label everything in there. And so I know my 90% CI is... low bound, we calculated out, 11.57. Upper bound, we calculated out. Wrong click, sorry. 11.8. Got too happy on my click. 11.87. And so there's your 90% confidence interval. We're going to have a nice sentence on that in the conclusion section. What I'm showing you is all the work you put into it, all the math you put into it. Then we're going to have a nice little 4 or 5 sentence in the end summarizing everything. So I'm doing all the work right now. So there's my 90% confidence interval. Please notice there's a certain number that's not in this confidence interval. You bet it, 12. 12 is higher than this upper bound. What does that tell me? Once again, I'm going to reject. Everything should line up. I rejected in the critical value, I rejected in the p-value, and I rejected with the confidence interval. My 12, my national average, my bottling average, is not really a national average, but it's my labeling average, right? I'm labeling the beer as 12 ounces. According to my confidence interval, with 90% confidence, I'm not making that label. All right, so that's another rejecting. 3 rejections in a row. It tells you we have an issue. We're shutting down the factory. We should all write that down in our big summary section. But we're almost there for that summary section. So what else would I kind of mention? Well, there's a couple things to kind of mention quickly. So, you know what? I apologize. I'm trying to think of how I'd ask it on a test. And there's 2 more questions to ask and I want answered, but let's put them in the summary. So what's the grand summary? Well, the grand summary would be all your statements. All right. First of all, I reject H naught. Why would I reject H naught? 2 reasons. My T statistic. Let's rewrite that number. So what's my test statistic? My test statistic, go back to beginning. My test statistic is negative 323. My test statistic is negative 323. Is in the critical region. That's the first thing I did, right? The first few steps. I found my test statistics in the critical region. My p-value. Getting the idea here? You built them. You take credit for it. My test statistic, my p-value. My p-value is 0.22%. My p-value is 0.22%. That is well under 5%, which is your alpha. That is another reason why I reject. So back to back, my t statistic, my p-value, both are in what I call in the critical region and under alpha, so I double reject. What does that mean? So I have evidence. I have evidence that supports the true, now it's time to talk, true average ounces of beer in the bottles is not equal to 12 ounces. So I have evidence that supports the true average ounces of beer in the bottles is not 12 ounces. And that's my report. That is not good. We should shut down the factory. We should maybe do a recall if it's really bad. We have to decide how bad it is. We're not giving the customer what the bottle says. We are clearly liable for the fact we're not giving 12 ounces of beer right now. We need to fix this. People have asked me, how do I deal with fraud? How do I deal with quality control? How do I deal with recalls? Here you go, guys. Right straight down the middle, this example. Right now, we're at this moment. What do we do, all right? We now know my machines are underfilling the bottles. How much? Well, that's what the thing is. That's what you state next. I am 90% confident that mu, which is the true average level alcohol, is between, and recite your work, 11.57 and 11.87 ounces. If you notice, I'm just summarizing everything we've just worked our behinds off, all right? I am 90% confident. You know what? Let's go back here. I have evidence that supports the average is not 12 ounces. And in fact, I'm 90% confident that the true average, if we actually sampled every single bottle we made today in the factory, the true average, that's what mu is, the true average, let's say we make over 10,000 bottles of beer in one day, fill them. I believe, I'm 90% confident that the true average is between those two numbers. Though, and the high number is clearly shy of 12 ounces. That tells me we have a choice to make now. Shut down the factory, do a recall, do what is necessary to make it clear that we have made a mistake at this factory and fix it for the customers. Customers are expecting 12 ounces. On the high end, we're not giving it. On the low end, we're really not giving it. It could be as bad as 11.57 ounces. Mu is somewhere between them. I don't know mu. Guys, I got bottles. I got over 10,000 bottles that have left the store, left the factory. I didn't check every one of them. I only checked whatever N was in this case. So this is my confidence interval. And I know on the low end, that's how much is on average in all those bottles that have left my factory. And so that is my conclusion. There are two things you can add. There's some additional comments you can make. Sometimes we make them, sometimes you don't. In research, the first thing you would do is you want to check your assumptions. What's your assumptions? Well, we're using the t distribution. That means we need normality. The good news is, if I recall, in this case, my sample set is 48. Notice N is 48. That's well over the 30 barrier for the central limit theorem, and that gives me normal, and I'm happy. Normal allows me to utilize the t distribution. What right do you have to use the t distribution? My right is my sample size is large enough. So guys, if you can pick your sample sizes large enough, do that so you get the central limit theorem to kick in for the normality. All right, that's very important to me. All right, my assumption, right? My assumption was, and I'm not going to write it there because I'm not going to automate it, but my assumption is that I have the central limit theorem. What gave me the right to use that statistic, the T statistic? It's because 48 is over 30, and I'm kicking into gear the central limit theorem. What are my two answers? Well, my critical value is in the rejection region, so I would reject. My p-value is less than alpha, so I'd reject. All right. What one last thing can we talk about besides the assumption? Sometimes the Cohen's d value is very important to us. What is the Cohen's d value? Well, the Cohen's d value is all about, are you sure the sample size did not give you your conclusion? Some people really believe sample size can really lend to the reason why you rejected or not rejected. So it's always good to say, if you worried about somebody saying, no, your sample size gave you your answer, you can come back to them and say, no, I checked the Cohen's d measure. What is the Cohen's d measure? Well, it changes based on your hypothesis test. The Cohen's d measure in this case will be x bar minus mu divided by s. That would be the Cohen's d measure here. So, and you can add this as an additional in your commentary, right? This is your summary commentary. And you can add in your commentary, hey, I checked my assumptions. Normality t-distribution is good. I checked in the Cohen's d, yes or no, sample size could be a problem. So let's check it out. Cohen's d. And let's automate it. So if we change the numbers in green, we can just quickly look at the new conclusions. So again, it's x bar minus mu divided by s. It's great to be able to automate these, so if you change one of the numbers into green, you could change everything quickly and just recalibrate your conclusion. And there is my d value, my Cohen's d value. By the way, Cohen's d should always be positive, so I'm going to take the absolute value of this number, which is 0.47. I should make that clear on my formula sheet, which it isn't, so I got to upgrade it. The Cohen's d measure is always positive, so we take the absolute value here, and the absolute value of that number is 0.47. All right, well, this is in the gray area. Sometimes that happens. This is in between 0.2 and 0.8. See, if it's under 0.2, there's clearly an issue with sample size. If it's over 0.8, there's not much of an issue with sample size. And that's what I got to mention here. Since, all right, it's between 0.2 and 0.8, there's a potential sample size issue. If it was below 0.2, there's clearly a sample size issue. Your results could definitely have been impacted by the sample size. If it's above 0.8, there is no sample size issue. So that's the number we look for. We try to get above a 0.8. We are at a 0.47, so we might have an issue with sample size. Well, all tests have their limitations, and that's what you could further talk about. Is there's a limitation in this study. We might have to rerun this study just to make sure that sample size wasn't an issue. We might have to resample a few other beers to make sure there truly is a, I mean, if I'm shutting down the factory and I'm placing a recall, I might want to redo this just to make sure that there are no issues. So in this case, I probably would want to resample because of the Cohen's d, because of it between 0.2 and 0.8, to make sure it is a reliable measurement. But I want to bring that to your point that sometimes sample size can control your answers. And how do you test for that? You use the Cohen's d measure. There are other measurements out there. Cohen's d is just an easy one algebraically to get at. As you can see from the formula, it's not hard. So there's our Cohen's d measure, and we would state, yep, we might have an issue with the sample size because this number was between the two critical values, as we call them, 0.2 and 0.8. Cool. That's how you would do a question if I asked all the way through with all the parts. I will always ask for what parts I want. You read the instructions carefully. What do I want? The critical value, the p-value, the confidence interval, the Cohen's d. What do I want? I will always articulate. In research, you got to decide what levels of details to put in. I'll put everything in. Why not? It gives checks, rechecks, triple checks. And of course, I write down the assumptions. And yes, I build a confidence interval if I reject. If I reject, I always build a confidence interval. If I do not reject, I really don't have a reason to build it. If I don't reject, I still pretty much trust that 12 ounces is what's in the beer. Because I reject, that's what I'm curious about. Where do you see it on the worst side and on the best side? On the best side, how many ounces do you think there could be? 11.86? Got it. On the worst case scenario, where is it? 11.57. Okay. So part A is done. All right. Part B and C, well, part C, do we have a quality control issue? We can already jump into this and say, yeah, we got a quality control issue. Part B is a totally different monster. We're dealing with a less than. And when you're dealing with a less than, some of these rules have to change, if not all of these rules have to change, because you're dealing with a less than. When you're dealing with a less than, certain things have to change in the test, which I'll get to in a moment. I want to mention, please notice, we have automated all the numbers below the green. So if you change alpha, for example, you say, maybe the boss didn't want 5%. Maybe the boss wanted a 10% test. Put in the 10%, watch the certain numbers change, and watch your answers change. Well, the alpha is based on the critical value. The critical value here, in this case, is now turned to 1.66. And notice 1.66 is the critical value. My test statistic is still over that critical value, which means I still reject. My p-value adjusted slightly, ever so slightly, but it's still ridiculous. And so, in the end, my p-value, all right, is still, my p-value is based on my test statistic, by the way. My p-value really didn't change. I apologize. I should realize that. And so my Cohen's d doesn't change. Right? Notice alpha really only affects the critical value and the critical value approach. I still rejected based on the p-value because my p-value is less than alpha. That's what I should have said. My p-value is still less than a 0.1, so my conclusion would still not change. All right? Let's change it back to the 05 part of the question. Notice the critical value is the only thing. My answers, I got to be careful, right? You always got to pause and think about your answers. This is my test statistic. It's not in the critical region. Sorry, it's outside of the critical region, which means you reject H naught. My p-value is clearly under alpha, and I reject. And those two line up. And you can play around with how the n changes, and then just pause and think about how everything changes in your answer. For example, let's say your sample size was 100. What happens now? Everything changes. Your test statistic gets even more critical. Your p-value gets even smaller. So I definitely am rejecting. Notice your d-value didn't change. Well, Cohen's d does not have to do with the sample size. It's still negative 0.46, and the absolute value of it is 0.46. So if I want to write this code correctly, I'd write in the absolute value in there. But my critical value, it also changed because my critical value is based, my critical value wouldn't change, right? My critical value is only based on alpha and n minus 1, not your n value. You got to understand what n plays with. N plays with your test statistic, your n plays with your p-value, your sample size plays obviously with your confidence interval. Clearly, these numbers are still under 12, which means I am rejecting. So all the way through, I'm still rejecting, even though I changed my n. Look how quickly things automate. What you still should do is take your time and think about what happens as you change these, what gets destroyed, what stays the same. All right, guys. So I want to quickly go through what if it was a less than test. How would I change things? Well, I wouldn't change anything here. Mu, alpha, n, x bar, s, they wouldn't change. Those are all part of given. My test statistic wouldn't change, right? My test statistic is based on my statistic. What would change is your critical value. Why would that change? Well, your critical value is now just one value. It's a less than test. All right, in a less than test, you have one bar. Where is that one bar? Well, you'd use t dot inverse to find that one bar. Now, that one bar has all of alpha underneath it. You would not share the alpha. And in fact, you would just use the alpha given up here to automate it. Comma, degrees of freedom, which is still n minus 1. Notice the upgrade I did to the critical value. Here, the t inverse, I use the fact that I am looking at a two-tailed test, and I found my critical value utilizing the fact that I have a two-tailed test. Or did I? Let me pause on that. Yes, I did because of the divide by 2. The divide by 2 showed the fact of how I would get it. So I did 1 minus that number in the t inverse. There should be an absolute value in there. Or there should be. Nope, we don't need an absolute value. Alpha is always positive, so I want to make sure my code is written right for you guys. So I'm always checking and double checking as I'm talking to you. Alpha is always positive, so when I plug alpha into here, t inverse of an alpha will always be negative. Why? Because, again, if you're looking at a less than, you're looking at the left side. If you look at the left side one tail, it'll always be a negative. So what's my answer in this case? Well, my test statistic is still under the critical value. My test stat is under the critical value, and so I reject H naught. That's what I would report. So let me shrink that down so I can fit that on the screen. Is again, my test statistic is clearly under, my test statistic is clearly under this critical region, and so that's why I reject H naught. Again, a slight tweak on this one, right? A slight tweak for part B is we go to a less than test. And let me be absolutely clear, because I did a great job up above, all right? So how would I change up there? What you would change is if you're doing the critical region now, your critical region's roughly the same picture, but there's only one bar. And that one bar has all of alpha now of 5%. And that T bar right there would be found by T dot inverse, because that's how I always find my critical regions, of the area below 0.5 based on your degrees of freedom to find the perfect T curve. And that's how I got the code to do it, because I understand the picture so clearly. Why the T curve? We've already been through the assumption. My sample size is over 30. We're good. Why the left side? Because we're doing a less than test. A less than test is the left side. Why 5%? Because that's the alpha. And all of alpha goes below it. Please do not cut it in half. There is no cut it in half in a one-tailed test. You give all of alpha. That's a slight little thing you got to be careful of. All of alpha goes underneath it. And that's why my t-value is negative 168. So my t-value is negative 168. All right, my statistic is clearly inside the rejection region. This whole area would be the do not reject. I'm here. My test statistic hasn't changed. -3 hasn't changed. I'm still clearly in the rejection region because of my test statistic. Awesome. All right, let's look at the p-value. Well, the p-value, let's look at the formula for the p-value. Well, that's got to slightly adjust too. My p-value is not going to be 2 times. My p-value is only on the left side now. So I got to understand and appreciate that. So, and in fact, it's just t dot dist of my test statistic, and I want what's left of it. So it's n minus 1 still for degrees of freedom, and I want what's left of it. The good news is the t dist gives you the probability to the left, okay? That's very important to me. This is the p-value in my example because that's the area to the left, all right? Again, the best thing to do is to go on and go through our steps. The p-value in a one-sided test, less than. Why was it less than? The question said less than. The p-value is to take your statistic. Remember your statistic, -323. That's your statistic. The p-value is the area below your statistic. That's the p-value. It's the area more extreme, to be clear. In a less than, it's the area under it, because it's a less than test. I need to know the alternative. The alternative is it's a less than test, which means I want what's less than it, and that's that area. That's the p-value. How would I find that? The code for the p-value in the less than test is t.dist. That's very important. It's not twice. I would only double it if it was a two-tailed test. It's a one-tailed test, and I want the less than. I would just drop this number in degrees of freedom, comma 1, because of how Excel works. And that's that number. And once again, I got my conclusion. My p-value is under alpha, so I reject. Can't spell. H not. Cohen's d has nothing to do with two-tailed, one-tailed tests. Cohen's d just says, is your sample size an issue? And it still is. Your sample size, is a potential issue. Let me use the correct words. If it was under 0.2, you clearly have an issue. And yes, let me fix this. The absolute value, right, guys? The absolute value. Cohen's d measure is always positive. So it's the absolute value in the measurement. And so, yes, that is not under 0.2. And so it's between 0.2 and 0.8. So I have some potential issue, not guaranteed issues. And there you go. But I still reject, which means maybe I want to build the confidence interval. And there you have it. The confidence interval is still good. A confidence interval is always double-sided. All right? So that's a double-sided confidence interval. 90%. You change the confidence level, we'd have to rebuild this to a different confidence level. If you want the 90% confidence interval, I have it built for you. So what happens if we change the different from a less than? Well, if our alternative is a less than, then that changes right here, the critical values and the p-values. It changes my critical values because I only have one tail. It changes my p-value because it has one tail. It all comes down to the picture. All right, that's why I always draw a picture in my steps so I can identify properly my t-values and my p-values. Yeah, my p-value is roughly 0. All right, I see that from the Excel code. That number is really roughly 0, 0.11%. All right, that's the number. 0.11% if you want the exact number. All right, guys.